Hello everyone, welcome to the second lecture on deep learning. In today's lecture we're really going to be looking at the foundational mathematical principles of statistics and of calculus, which will lead us into the backpropagation algorithm. So deep learning is a field, as we've briefly mentioned before, which is driven by an explosion of new papers each year. I've just finished reading the latest batch of ICLR papers. There was about 3,000 submissions, and you really need to develop a skill to very quickly open a paper, glance through, maybe briefly read the abstract and just look at the key equations and figures, and then you can recognize the big operators and say, I know what theory this is building on top of, and that will help you sort of focus in and see where the contributions are. So it's a very important skill to develop. And I appreciate that a lot of the notation and concepts in this lecture will just be a recap for some of you, depending on which prerequisites you've taken. But it's always helpful to revisit this stuff through a deep learning lens. And there might be some people watching this who have a weaker maths background, and you might find this lecture quite challenging. And for those of you, I suggest you look at the reading list and you open up NumPy and create some example smooth functions and play with them according to the definitions. There's also Desmos, which is a graphing tool you can use online, and you can plug in a lot of the equations into there and you can see them and play with them, play with the variables and so on. So this will lay the groundwork for the backpropagation algorithm, and it will also be useful in the reinforcement learning lectures where we'll use a lot of similar kind of statistics and notation in that. At the end of this lecture, you should be a lot more confident with the notation and mathematical language used in these deep learning papers. So we're going to start with a simple revision on distributions. Specifically, we're going to just define what a probability density function is. So the probability density function, or the PDF, is a function which maps from Rn, so some n-dimensional real space, just to R, so to a single value. And it describes the relative likelihood for a random variable to take on a given value. Okay, so a random variable we'd normally denote with a capital X taking on a given value like a little x. So in this simplest case, where we're just talking about a one-dimensional case, so n equals one-dimensional case here, R1, you can visualize this just as a one-dimensional function. But the properties are that all the values in this function must be non-negative. They must, and also its integral exists where adding up all of the values in this function, it must integrate to 1, so it must sum to 1. Okay, so the area under this curve, it integrates to 1. So with just like a simple example, let me just switch to my notes. So if I get that. Okay, let's just start with a really simple normal distribution. So we could say that the mean height of people in Durham, we could say the mean is mu is equals to 178 centimeters. And we could say there's some standard deviation, sigma is 8 centimeters. So that's like, imagine everyone in Durham is some population. Let's just try and draw this. Here's like just taking some samples here. So if we have like height on the y-axis here, height, and we just take some samples of people in Durham, maybe like here, here. There's a shorter person here, a very short person here, but most people are going to be sort of centered around a normal distribution. Maybe there's a very tall person here. So if we plot this, if we plot the distribution over all of these observations of people in Durham, we'll see that the mean is sort of 178 centimeters. And if we parameterize this normal distribution, so we say it's parameterized by function f of x, conditional on the parameters, so mu and the standard deviation, sigma squared. We have this normalizing constant which ensures it integrates to 1, which in this case you can get this definition off Wikipedia, but it's just 1 over 2 pi sigma squared. And then we have our definition, exponent 1 over, just trying to remember, 2 sigma squared, and then we shift it by the mean, so we say x shifted by the mean. So that's just a definition of the normal distribution. Here's the mean here, so we shift x by the mean, we sort of move it that way. So I'll just try and make sure my notes are better centered. Shift by mean, and then you very commonly see some like 1 over before the actual function here, and this just ensures that the whole function integrates to 1. So this is like this normalizing constant. Okay. and this ensures that the integral of f of x over x equals 1. Okay, so when you have this this function, this probability density function defined, you can answer questions like, you could say, what is the probability of someone being between 180 centimeters and 190 centimeters? So you would write that as integrating where the domain is 180 to 190, f of x over the space of x. That would give you some, so if we were to plot this, this would be like saying, what is this region here, the area of this region here. If you compute that area, you'll get some value like 0.334. So it's about a third probability that you would find someone being between that height, between 180 centimeters and 190 centimeters. So if you asked a similar question like, what is the probability of someone being between 210 and 250 centimeters tall, you know, that's like somewhere crazily in the tails of distribution, and it's very, very unlikely. So you can actually just plug that into Desmos if you want to see it. You should write this 210 to 250 f of x dx, and that would give you something like 0.000003. It's very, very, very unlikely that you would find someone this tall if it's modeled by a normal distribution. So let's just switch back now. Okay. So this is just looking at it in the continuous case, but we can also look at the discrete case, in which case it's called a probability mass function. I'm just reading the slide. It's the same conditions, but we basically just replace that integral. You just replace that integral with a sum. So all of the, here's an example here. We generally tend to use capital P here. So we just say we sum up all the values of this random variable, taking on the actual values, the discrete values here, xi, and we make sure that adding up all of these values adds to 1. So if we use, like in the previous case, normally we would use like a little p to denote a continuous variable, or over a variable whose type has not been specified. But in the discrete case, normally we would use the notation of a capital P to notate a probability mass function. So in the figure we have two probability mass functions, and each has been sampled from an underlying continuous Poisson distribution. So this is just a distribution where you can change this parameter lambda, and we've got here two cases where we've got lambda equals 1 and lambda equals 5. But if you sum up all of the discrete variables, the observations, you'll see that these values all sum to 1. So it's a probability mass function. And in most of this lecture, I'm just going to work with continuous definitions, as it's easy to see that you could just replace that integral with a sum for the discrete case, and you'll get like an equivalent probability mass function. A lot of the time in the reinforcement learning literature we'll be using the discrete case where we have discrete action cases, but you should know that it also generalizes to continuous action spaces just by replacing the sums of integrals. So now we're going to introduce the joint density function. The joint density function models the probability of two or more random variables. So for example, if you have the age of people in Durham in a spreadsheet, and also the height of people in Durham in a spreadsheet, so you can imagine lots of observations of everyone's age and of their heights, we want to learn the relationship between these two variables. For example, you can imagine how a child who's very young will not be as tall on average as an adult, so there's some relationship between them. And the joint density for a pair of random variables is a natural extension of the probability density function for a single variable. So it's also a non-negative function, so all of the probabilities that you observe inside are non-negative, and also all of them must integrate to 1. So all of the probabilities from the both variables must integrate to 1. So in this case here, you could imagine like x being the age and y being the height, or something like that. And the probability defined of both these random variables must integrate to 1. And this is the definition here. It's just saying that the joint probabilities between x and y within some region A is the same as integrating over that region A for the two random variables x and y over the entire space. And this generalizes to what's called multivariate joint density functions, where you have lots and lots of variables in here. You can have n-dimensional joint density functions. So you see these two distributions over here. They're called the marginals. So you can actually factorize a joint density function into a product of its marginals, which is really useful because if we can somehow compute these in deep learning, we can compute the joint density. And the joint density is really our goal a lot of the time. If you go back to our spreadsheet example, if we've learnt the joint density between the ages and the heights of people in Durham, it means we can actually sample from these densities, from this joint density function, which means we can generate new samples which are likely, so we can create a new population or a new space of samples. So it's a generative model, really. So if we've learnt this distribution over, say, all of the pixels or images in a data set, so with 1,000 squared images as all of our independent variables, and that means we have millions of dimensions here, millions of variables, x1 all the way up to xn, then if we've really learnt that distribution, we can actually sample from it, so we can generate new images of faces and so on. So these are called the marginals, and they're really useful if we're able to compute them. And to compute the marginals, the marginal density variable is found by integrating out the other dimensions. So if we look at this marginal here, it's infinite. It's integrating over the whole of space, so the whole domain or the region where the probability density is defined, and it's found by integrating out the other ones. So if we're after this marginal here, which also integrates to 1, you can imagine it like summing over this direction over dy. If we're after, it's actually over all of the other ones. So if we're after this marginal here, it's summing over all of the other dimensions, of projecting it this way. So it's probably worth me just showing this in the n-dimensional case, just so you can see how you integrate out the other dimensions in higher dimensional cases. So if I just switch over to my notes, hopefully that's in the view. If say we've got lots of random variables like age, height, and weight or something, all the way up to sort of xn, then let's say you wanted this marginal here, f of x1, this marginal density, then you have to again integrate over the whole of the space for all of the dimensions, so from negative infinity to infinity. Sorry, that's meant to be an infinity. And then you have to do this for all of the random variables, x1 all the way up to xn. But this time we only integrate out the other dimensions. So we do, if we're after x1, then we do dx2, dx3, dx4, and so on all the way up to dxn. So therefore we have n-1 integrals over the joint density function to get the marginal distribution of x1 alone. So in example question, let's say we want to learn the joint distribution, or I'll just write it, what is the joint distribution of ages, weights, and house values and we could say, like, we have a spreadsheet where we've got like 5 random variables, so we've got like 5 columns, and we've got, like, I don't know, x1, x2, x3, x4, x5. Actually, I'll just write it out here. So we could say x1 equals the age, and this is of people in Durham, and this is, like, I don't know, we could say 0 to 150 years old. Sorry, I'm not sure if my notes are in view. x2 is the height, and we can create some intervals, say 0 to 5 meters. X3 we could have as the annual profit. And this could be like unbounded, I suppose. You could even make a loss, so we could say it's between negative infinity and positive infinity. This is an unbounded interval, so, and that can be in pounds. Then we could say x4 is, say, the weight, and this can be in kilograms, maybe, I don't know, 0 to 1,000 kilograms. And finally, let's have x5 is like the house value, equal value of house. And again, we could have that as sort of net 0 to infinity. It can be unbounded on the infinity case. So we want to ask this question: what is the joint distribution of the ages? That's x1, the weight x4, and the house value is x5. So we want to find its marginal distribution of x1 and x4 and x5. So therefore we would say, if we want, we have to therefore integrate out, if we want, so it's the marginal distribution of x1, x4 and x5, x1, x4 and x5. So we need to integrate out x2 and x3 to compute that. So we would say the marginal distribution of x1, x4 and x5 and then we integrate out x2 and x3, so we actually go the other way, so we go just doing inside out infinity for the profit, and then for 0.5 for the height, so that's over this domain, and then we're going to put in, we have to do this for all, evaluate for all variables, so it's going to be f of x1, x2, x3, x4, x5, but we're going to only integrate over dx2 and dx3. So that's what we would do, we'd integrate out the other dimensions. So you can sort of get rid of variables simply by integrating them out. Okay, so the next really important thing to be able to do is to know about conditional density for pairs of random variables. So this slide really introduces what conditional densities are. And if you look at the definition or you look at the equation, you'll see it's the density for a random variable conditional on, so little x, conditional on some observation of another. So we observe conditional on y taking on the value little y. And this is actually equal to the ratio of the joint density of both random variables in the numerator here to the marginal density of the conditional random variable in the denominator. And this allows you to answer questions like, what is the probability of y of a person's age, given that we know that the random variable x, their height, is 1.4 meters. So if we know someone's height is 1.4 meters, what is the probability, the distribution over their age? So that's a really useful thing to be able to do if you have some observation of some data and you want to learn all of the other marginals, or you want to learn all of the other things, so you can sort of build up given some partial observations. So working through like some example, we could say like, let's go back to my notes. Okay, so again, let x be the height and let y be the age. We ask the question, what is f of y conditional on x? So we would say y given x, the random variable x, taking on some observation, and this, according to the definition, is equal to the joint density of both random variables, so f of, sorry, I've done this wrong. F of x, y. I'm doing the full no abuse notation here for the marginal f of x, and then we would say, so we could say this is f of y given x, and we could say y of x taking on the value 1.4 meters. We want to know this density, so we would say this is equal to 1.4 times the marginal of the age over marginal of the height f of x of 1.4. And this actually gives another, if you look at the slide, this actually gives another 1D distribution, which is the probability of the age. And in this example, the most likely age, or if you like, the mode of it, is about 10 years of age, 10 years old. So if someone's that 1.4, then they're most likely to be about 10 years old. And if you queried the resulting distribution at 20 years of age, then the probability would be near zero, as very few 20-year-olds are that short. So you'll see that you can actually recover the joint distribution from an observation and the marginals. And if you need convincing, I recommend like the exercise of constructing and plotting two smooth functions that integrate to one as numpy arrays, so like between 1 and n to 1. And you can have these as your marginals, f of x and f of y. And you can just like simply multiply them together to get your joint distribution, which in this case will be a matrix of the two variables. And you can check that the marginals and the joint probability all sums to 1. And you can try out some of these formula indexing the marginals at the value of the observation. So actually there's like a link on Duo to doing some of this, where you can play with these. Okay, so this brings us on to the expected value. The expected value is a bit like an average of the variables. So the mean, or the expected value of a continuous random variable x, is calculated by integrating the product of the probability density, so f of x, of little x, with all of the values in its range, little x. So similarly, the expected value of any function of a random variable is computed by integrating the product of the density at all the values the function takes over the random variable's range. And it's important to see this is not the same as the mode, so you can see in the diagram here. You can think of the mode as the highly probable samples, such as like hyper-realistic faces. And often learning the expected value of faces will just result in like a blurry image, which is improbable, but it's the average image. And often maybe I could just show you some common notations. Often in deep learning, you'll see notations like, we'll say that the expected value of some variable sampled from some distribution, n of mu and sigma squared. So this is like from a normal distribution. And you'll see this notation. So this and basically the expected value of this normal distribution, if you remember from our example, maybe I can just quickly draw it here. We've got some normal distribution. We just randomly take samples and we just keep averaging them. If we take the average value of all of these samples, we'll see it is actually, in the case of a normal distribution, equal to the mean. So it's equal to mu. Or you might see notation like for a function, so we could say like the expected value of x from some probability density function f of x. And this, you would read this as the expectation of f of x with respect to this probability. And if you define the probability p of x to be the data distribution, or if you like the entire data set or data space of all data in the observable world, this means just simply like drawing samples that follow that data distribution. So for example, just drawing samples from a data set. For example, like if we could say our loss, this is a common thing to say in deep learning, we could say our loss function is equal to the expectation of drawing some sample from p or p data, and then you could just have like your the thing you minimize. So in this case we could just do like an L2 norm, f of x minus x squared L2 norm. So this is just like saying we minimize this error here, drawing samples of x from our data distribution here, feed it into our model, we get some error term and we minimize that. So that's our loss, our objective function. And on average, this is just like a big averaging over it. So on average, this is what we would expect to get the loss to be. So a discrete case, maybe a simpler case, we could say like, what is the expected value of throwing an unbiased 6-sided die? So a die has a probability mass function where there is equal probability of taking on each of the 6 values. So you can imagine just throwing it. So we can just replace the integral with a sum in this case. So by the definition on the slide, you could just replace that. So you could just say, let me just get a new piece of paper. Just say the expected value of x equals summing I equals 1, and then we would just do x times the probability of order little xi. So let's just do this now. So it's the value of the die times the probability, and in this case this is just like 1/6 because it's a 6-sided die. So we would say a die is from a uniform distribution, it's not biased die, it's not like you can cheat with it. Okay, so this is just going to be equal to 1 times a 6th plus 2 times a 6th, 2 plus 3 times a 6th plus 4 times a 6th plus 5 6th plus 6th times a 6th, which is equal to just 1 plus 2 plus 3 plus 4 plus 5. So do that all over 6th, which is actually equal to 3.5. So on average, as you throw a die over an infinite number of trials, you will eventually converge to a value of 3.5 as you keep averaging. So that's kind of like the really foundations, and you'll see like expectations a lot in the literature, and hopefully you'll get some comprehension of probability density functions and joint probability density functions, marginalization, and conditional density. It's very useful to have those skills as we move on to the more advanced generative models. Okay, so that concludes a very brief introduction to foundational statistics. Now we're going to move on to foundational calculus. And we're going to start by just recapping the basic definition of a derivative, where it's like the slope of a function. Then we're going to extend that definition from real valued function to vector valued functions, which are typically used in neural networks. So differentiation is the operation of finding the derivatives of a function, and the derivative of a function measures the sensitivity of a function's outputs with respect to changes in the inputs. So in deep learning, we wish to modify a neural network's parameters, such as to minimize error in the network's outputs. Therefore, we need to calculate derivatives to do this. So the formal definition of a derivative is defined as a limit value as the ratio of the differences, as the differences tend to 0. So a limit is basically like imagining where things are heading. If we take some value to 0, we can basically observe it at, say, values greater than 0, but we kind of imagine where it ends up as it goes to exactly 0. So in this figure here, if you look at these two observations of this function with h, and you imagine like taking h to smaller and smaller as this triangle gets smaller and smaller and smaller and smaller, you end up with a tangent line. So this line here ends up as like another function whose slope is actually the derivative. So you can imagine this tangent line can kind of go up and down, and the slope of it is actually the derivative. So for more intuition, I recommend you visit desmos.com/the calculator, and you just graph out some common derivatives. So you can type like f of x equals tan h of x. Then you can just like do f dash of x for the first derivative, or you could type like f dash dash of x for the second derivative, and so on. So that's quite useful notation. You can also use like d over dx f of x to see them, but it's more convenient, I think, to just write it like this. So if you recall from like the first lecture, we said that a neural network or artificial neurons, they contain this weighted summation followed by a nonlinear activation function. And so here's some like common nonlinear activation functions here. You can see the rel u1 in red, which was the max of 0 and x. And these are some, on the left, these are some useful derivatives for like the common activation functions. So rel u, the rectified linear unit, if you imagine, well, we can see that just in red here, this is just the actual function itself, not the derivative, but the slope of this, or the rate of change of this, is just 1 everywhere. And for 0, it's got no slope, so it's 0 everywhere. So if we were to plot the derivative of the rel u of x, it would just be like 0, 0, 0, 0. And the second it gets positive, it would just step up to 1, and then it would be a flat 1 everywhere. So you could have a go plotting that in Desmos if you want to see what these look like. Just briefly, maybe if I flick to my notes, just to mention a couple like special cases, which I'm sure a few of you will know already, but just in case. So e to the x is e to the x. If we look at the first derivative of e to the x, we'll see it's actually e to the x. So this is a funny case where the derivative is actually the same as the function itself. So all of the derivatives are the same as the function. And another interesting case, which is useful to know, is if you've got like a periodic function. So if like you say f of x equals sine of x. So sine of x is periodic. If you plot it, it sort of repeats forever and ever and ever like this. And it's got this period, which is 2 pi. So the repetition period is 2 pi. So we could say like the period L equals 2 pi. And if the function is periodic with some period, then you can always say its derivative is also periodic with the same period. And that's very useful to know. So like with sine of x, if you look at it, all of its derivatives, you can say like sine of x, the first derivative of sine of x is cosine of x. The first derivative of cosine of x equals minus sine of x. And the first derivative of minus sine of x equals minus cosine of x. And then again, if we were to like plot the fourth derivative, so you could equally say this is like sine second derivative of x. You could say this is sine third derivative of x. And therefore it's going to come back on itself now. So we'll say 1, 2, 3, 4, and that's just going to equal sine of x. It's good to sort of memorize these and get familiar. So it's sine, cosine, minus cosine, sine, cosine, minus cosine, and so on. Okay, so coming back. So now we're going to just kind of run through the basic rules of differentiation. And these are like on the left here, the main rules to differentiate real valued functions. And I'm not going to read through all of the definitions just to save some time, but instead we're just going to jump straight in with some examples, and then we're going to just use the rules in the examples. So let's say we want to differentiate this function here, h of x equals sine of x squared. What we need to do is we need to like first break it down into two functions. So what we're going to do is we're going to start by just looking at the outer part, and then we're going to look at the inner part. So we're first going to just look at the outer part and say the outer part is just g of x is equal to sine of x, and then we're going to say f of x, the inner part, is equal to x squared. And then what we'll do is we're going to calculate the derivatives respectively for the outer parts and the inner parts, and then we're going to substitute them in together and use the chain rule. So let's start just by doing this. So we'll start by just saying the derivative g of x is equal to cosine of x. So if you remember, we just said before, it goes sine of x, its derivative is cosine of x, its derivative is minus sine of x, and then it's minus cosine of x. So the derivative of sine of x is cosine of x, and for the derivative of x squared, we're going to use the power rule here. So the power rule is basically where you take the power and you bring it down here. So you go from x squared to 2x. And now we've got these two derivatives here. We've got the derivative of g of x and derivative of f of x. We can substitute those into the definition of the chain rule. And this gives us cosine of x squared times 2fx. So it's worth saying you might want to try some more examples out. Maybe pause the lecture here. If you've not had a lot of practice doing this, create some new functions, try and differentiate them, and then you can actually type those into Wolfram Alpha, and it will often just show you the derivatives as it gives you the results. So just like type this into Wolfram Alpha, and then you should see it will give you something like this. So you might want to just test and play till you're really confident doing that. So now we're going to we've seen how to differentiate any univariate function. So these are functions which map from just like r to r, from a single value to another single variable. But we need to learn to differentiate multivariate functions, which are functions of more than one variable. So in this example on the right, we have some function which has two inputs, f of x and y. And if you solve it, you get an output that maps from r2 to just a single value in r, which is like the surface of this function. So the function admits two partial derivatives. It has a partial difference f of x with respect, the partial derivative of f with respect to x, and it also has the partial derivative of f with respect to y. So let's just write this down and try and make it clear. If I again go to my notes, I might just get a new pen to turn it over. So let's just write the function out here. So we've got f of x y equals 4x plus 7y squared. And according to the definition, we get two partial derivatives. So we get the partial derivative of f with respect to x, and we also get the partial derivative of f with respect to y. So that's kind of how you read it. You read this as the partial derivative of the function f with respect to x, and this is the partial derivative of f with respect to y. So to actually differentiate this, what you do is you look at the variable in the denominator here that you want to differentiate with respect to, and you see if it exists in any of the terms. So you've got these two terms here, and does x exist in any of these terms? Well, it exists in this term, but not in this term. And then you basically, if it does exist, then you have to differentiate that part, and if it doesn't, that's just a 0. So let's just differentiate this side here and we'll keep the other variables which are present. So here we just say the derivative of 4 of x is just 4, and then it's plus 0 because there's no x in here. And similarly here we would say there's no y in this term, so that's just going to be 0, and then it's going to be, and then we just differentiate this, which is 14y. So another example, just to make this clear, if you look back at this slide, we also talk about it gets all of the partial derivatives get collected into a row vector known simply as the gradient. So here we've got like these two partial derivatives, so you can imagine just putting them together into a row vector, which is called the gradient. So let's just see another example now where we're going to say calculate the gradient of some function with respect to x. We could do it with respect to other variables, and the function is going to be for f of, this is going to be a free variable function with 3 inputs, and we're going to define it to be cosine of x plus z cubed, and then we're going to say minus x squared y. So you might want to sort of pause the lecture here and see if you can have a go at this yourself. But it has 3 inputs, so it admits 3 partial derivatives, so we're going to just write them all out. So we're going to say the partial derivative of f with respect to x, partial derivative of f with respect to y, and the partial of f with respect to z. Okay, and in this case we're just asking for the one with respect to x, but I might as well just do them all. So to do it with respect to x, we're going to first say, does x exist in any of these 3 terms? Well, it exists in this one here, not this one, and in this one here. And then we're going to differentiate each of those terms separately. So do you remember the definition of cosine of x? We said it went sine of x, cosine of x, minus sine of x, minus cosine of x. So the derivative of cosine of x is minus sine of x. So we're going to write out minus sine of x. And then there's no x's in this term, so it's plus 0. And then there's an x in this, so we need to differentiate this. And again, we're going to use the power rule, so it's just going to be minus, so it's plus minus, which is actually minus 2xy. And we might as well just do it for the others briefly. So this is just going to be, there's no y's in here, so this is going to be 0. There's no y's in here, so that's going to be 0. And then there's a y here, so it's differentiated. That's just going to be minus x squared with respect to y. And this one here, again, there's no z's here, so this is going to be 0. There is a z here, so that's differentiated with respect to z, so that's going to be power rule, so that's 3z squared. And this is going to be minus 0. So for functions with lots of inputs, like a deep neural network operating on images, we're going to collect all of those partial derivatives into a row vector, which we call the gradient of the function with respect to all of its inputs with respect to x. So yeah, I recommend you visit Wolfram Alpha and type in some more multivariate functions and see if you can differentiate them. Okay, so there are the rules of partial differentiation, and just like the rules of differentiation, I'm not going to read through all of the definitions. In fact, let me put my projector back. Okay. So I'm not going to go through all of those definitions, but you can keep it as like a reference, I suppose. And these rules are actually the same as the rules of differentiation, but instead of just like having f prime or f dash of x, we just write out the partial of f, or partial derivative. Oh, sorry, didn't mean to click that. The partial of f with respect to x, partial derivative of f with respect to x, or you could write the function, take the function, and instead of putting it up here, you can just put it here. So this is the partial derivative of this some rule here with respect to x. Okay. And note that in this slide, the x's are in bold. So this means our gradients now involve vectors and matrices. So matrix multiplication, as in the chain rule, is non-commutative, which means that the order really matters. So I've been caught out many a times if you've just done things slightly the wrong way around and you're actually doing matrix multiplications, you'll get errors and crashes and all sorts going wrong in your code. So a minor comment, you may see the notation like this, so just bear in mind that does mean the partial of whatever function it is in the brackets with respect to x. So do remember that when you come across it like this. So you might want to sort of read through this nasty example and make sure you understand it. So I could give a short example just in my notes. So let's just again go down. Right, so just a short example. Let's say you've got partial derivative of some function 3y x squared with respect to, let's just do it with respect to y. This would basically mean the partial derivative of 3yx squared with respect to y. And in this case, we would say all of that is just 3x squared. Okay, so in the previous example, we basically looked at differentiating functions of the form Rn to R. So they always map to a single output. But what if we want to extend our definition to differentiating vector valued functions? So this is where we have some domain Rn mapping to a codomain in Rm. So a different, you have different number of inputs to outputs. So this is actually quite an easy extension, but basically you calculate the partial derivatives for each of the functions individually with respect to each of the inputs. And this actually gives like an m by n matrix of partial derivatives. So consider this like example function here. This actually parameterizes a three-dimensional helix curve. And the function has two inputs, t, which is like your time along the curve, and I also added an input s, which is like some translation along, I think it was the x dimension. So you could like move the curve around, and you can also translate where your t is along the helix. So it has two inputs, which parameterize those things, and it has three outputs, which correspond to like the Cartesian x, y, and z coordinates of the space of the helix. So it maps from R2 to R3. And as you increase t, then the x, y coordinates that you get out, the point that it outputs, will be in a different place. This red point will be in a different place. You'll get the x, y, z coordinates for this red point as you move t around. Okay, can you visualize that? And if you move s around, then it just moves the entire helix along translates this whole spring like along the x-axis, so it sort of moves it this way. That's what the function is defined to do. And the question we're going to ask is calculate the Jacobian for this function with respect to its inputs, with respect to t and s. So that's what we're asking. And the Jacobian is an m by n matrix, and in this case it's a 3 by 2 matrix because it's got 3 outputs and two inputs. So I'm going to just write it out and do this. So if I put this down here, so I want the Jacobian of that function. I might as well just write out the function. So f of t and s equals, it's a vector valued function, so it's got x is equal to sine of t, I better make a mistake, plus s, we've got our translation in there, then y is equal to cosine of t, and then we're going to say z is equal to 6t over pi. We want to calculate the Jacobian of this with respect to t and s. So we said it's an Rm by n matrix, where we say the Jacobian of this function is equal to, let's give ourselves some space, so let's write out all the partials. So we got the partial derivative of sine of t plus s with respect to t, partial of cosine of t with respect to t. Probably should have given more space. And then we're going to say the partial of, let's just do the function here, so 6t over pi with respect to t. And then we're going to go partial of sine t plus s with respect to s. Okay, and here partial cosine t with respect to s, and then lastly okay, so partial of, I'm just going to write it here again, 6t over pi with respect to s. Okay, so to differentiate, we have to now differentiate all of these, so I'll write it out. We could write it equals here and put it there, but I've not got much space, so I'm just going to write it again here, the outputs for this. And in this case, we have to go through each of the terms. So in this case, does t exist in this term here? Yes, it does. Does it exist here? No. So this is just going to be, what is the derivative of sine of t, sine of x? Remember, it's cosine of x. So this is just going to be cosine of t plus 0. T doesn't exist in this term here, so we could just leave that as cosine of t. Now let's do it for this case here. So again, t, there's only one term here. Yes, it exists there again. What's the derivative of cosine? So it goes sine, cosine, minus sine. So this is just going to be minus sine of t. And here we're going to differentiate and go what is it, is t in this part here, is just going to all come out to 6 over pi. And then it's a lot easier in this case here because s only exists in one of these terms. So does s exist up here? No, so that's 0. And then here it does, so that's just going to give us a 1. And then s doesn't exist here, so that's 0. And s doesn't exist, sorry, Mr. Brackets in here, so that's 0. So that's the answer, that's the Jacobian. So here's just an example of this. Consider a neural network with one linear layer like before, so we just have a function of x, and that's just a multilinear map where we multiply the weights matrix by the inputs x and add some bias term. And then we're going to have our loss function or our error function for determining whether those 3 predictions are any good as a squared L2 or Euclidean norm. And this is just simply summing the squared terms, so it's just squaring all of those outputs and summing them. But we're going to use this in a way to actually measure the error to some target labels, so like some ground truth labels or predictions. So the network loss function is just a function which maps from its n inputs, and at the end of the day it just has a single value as its output, the cost of the whole thing, or how bad the network is for its predictions. It's very important that we always just have this single output. As we'll see later, it's computationally a lot more efficient. So we can just say that the loss is just like a classifier really. You take some neural network which has some inputs, maybe some pixels, or it could be some just any kind of inputs, and it gives you these predictions as outputs of this function here. And then we subtract, we find the differences from some target or some ground truth where we say this neuron should be 1 because it's actually a horse, and the others should be 0 because it's not a dog or a cat. And then we take the squared Euclidean norm, which is like the distance between the output and the prediction, and we can just like substitute this function with our definition for the multilinear lap here, wx plus b. And this can actually, if we were to actually implement this, we can model it as a computational graph. So I've shown how that graph might be implemented here. So it's a directed graph, and the nodes are the operators, and the variables are fed into the nodes. And the output is just the loss, which is a single value that we wish to minimize. And the example graph you see is just an extension of like the previous slide. So instead of summing the outputs, we actually have the actual loss function, which measures the output squared Euclidean distance between the predictions and the target labels t. And what we want to do is compute the gradients of the loss with respect to the network parameters, which are the leaf variables w and b. So we want the gradients here. And in PyTorch or a modern deep learning library, you would just make sure these variables have the variable .grad required equals true. And for we don't really care about the gradients of the inputs in this case. In some applications you might, so you can just make sure this has grad required equals false here. And then what we do is, if you've been following everything so far, to differentiate the loss with respect to w and b, the obvious approach would be to start at the inputs and work your way down, the graph. But hang on, if x has say like 1 million values, like just a medium-sized image, and let's assume like the next layer is the same size, then your Jacobian, if you think about it, will be a 1 million by 1 million sized matrix, which would require 1 terabyte of memory. And this is like called the forward accumulation strategy, and it would and it's just not very good. It's just not feasible. So it would be very efficient if the network had 1 input. If the network just had 1 pixel as input, then the forward accumulation strategy would be good. It would just it would be computationally efficient. But with lots of inputs and just 1 output, it's just not a very suitable way to approach. So we can say forward accumulation is efficient if you're mapping from Rn to Rm, where n is much less than m, because in that case only n sweeps are necessary. But instead, in like 99% of deep neural networks, we wish to minimize the projective loss function, which conveniently only has a single error value. So we need a different strategy for this. And this is introduced in what's called the reverse mode of automatic differentiation, or reverse accumulation. We use backpropagation. And this is actually a dynamic programming approach, which we'll discuss in reinforcement learning. But it does the least amount of computation in cases where m, or your outputs, are much less than the number of inputs. So just reading through what you would do, you would set requires grad to true for any parameters we wish to optimize, in this case W and B. And then you would calculate the loss by a forward pass. So you would first just like feed your inputs through the neural network. And when you're doing that, you're going to be saving some intermediate values, which you're going to use later. And then from that loss, you would do dot backwards on it. You're going to traverse, you don't actually manually have to do this, the tooling will do this for you, but you're going to have to reverse to accumulate the derivatives of the loss at each of the leaf nodes. So after backpropagation, we can adjust all the parameters in the direction of the negative gradient to optimize our neural network. So just briefly, if I just zoom in, okay. So just briefly, if we say our parameters theta, and in this case they just consist of the weights matrix and the bias vector. And what we want to do is we want to just say we're going to update all our parameters just in a little bit in the negative, that's alpha, in the direction of the negative gradient. So we're just going to negative, take the partial derivative of the loss with respect to all of our parameters, theta, and we're just saying like move every parameter a little bit up and down such as to minimize the overall loss. And it turns out that that strategy, if the network does only have one output, just like we saw, is surprisingly just of similar complexity to the forward pass itself. So just like computing whatever functions you have. You know, it's quite easy to compute like the actual functions, doing like a weighted sum wx plus b. Actually just doing that operation, turns out that differentiating is actually of the same complexity if you just have one output. So that's kind of counterintuitive considering how complex the expression of the partial derivatives is, where you have to do all of the chain rules and power rules and breaking it all up and doing it. And the fact that we would need to compute so many of them with many layers with millions of parameters, and considering how easy it is to implement f of x. So yeah, Ian Goodfellow once tweeted that he can't imagine that in cases where backpropagation can be used, there will ever be a more efficient algorithm. So we kind of can say it's here to stay. All right, well that kind of concludes a kind of brief blast through foundational statistics, foundational calculus, and moving on to backpropagation. Thankfully, a lot of the tooling does a lot of this for us, but it's very useful to understand the fundamentals and how it's going on under the hood. If you want to really get a deeper understanding of these topics, I strongly suggest you have a look at these recommended books here. So if you've forgotten some of the maths or are confused by any mathematical notation or concepts, I recommend Mark Dijzenroth's Maths for Machine Learning book. It's well formatted, it has lots of examples, and it doesn't go crazily beyond the foundational maths required in machine learning. It's a very good recap. Ian Goodfellow's book is very famous. It's a bit too waffly for my tastes, but I recommend just scanning through it, and if you see anything interesting, then just examine it a bit closer. It details, it has really strong details of the implementations of backprop, and if you enjoy sitting down and reading through lots of text, then it's got quite a good broad coverage of many topics in deep learning. It's starting to get a little bit dated now, but it's still quite comprehensive. And lastly, if you want a much richer mathematical understanding and knowledge of the field and are up for a real challenge, I recommend a video, Carlin's Deep Learning Architectures, a Mathematical Approach. This book goes far beyond the level of understanding you can get from following tutorials or online and reading Wikipedia. It's got lots of proofs, formal analysis and network capacity and on the connectivity between deep learning and geometric theory. It's a real masterpiece, but it is a hard read, but it's very rich and rewarding if you can get to there. All right, well that concludes this. Have a good week.